So before I start, I want to sort of credit people who have helped me along. So Shai Ben David is a professor at Waterloo. Kobe Kramer is a postdoc in our group. Mark Dredzy actually, I think, interned with you guys last summer in New York City. Ryan McDonald was a fellow grad student, is now at Google in New York City as well. And Fernando is my advisor. So the problem I'm going to talk about is hopefully one that anyone who's ever worked with statistical models has encountered in some form or another. And that's that you train up a model in the lab with the data you have, you test it out, it looks pretty good, and then when you go to apply it in the real world, it's just terrible. Right? And so this can happen in vision, where you have cases where you may have good face data at train time, but when you go to apply a face recognizer, you might have occlusion or lighting differences that you need to deal with. For gene finding now, this is becoming exceptionally important because you may have good, well-curated, annotated DNA sequences from one organism, but you want to train a model that works well for a different organism. And probably, probably the most familiar setting to people here is in speech, in speaker adaptation, where you have transcriptions from one person, but you actually want to use a speech recognizer in a case where a person has a very different accent or vocal tract length. Okay, so in text, this problem is particularly acute because there's really a huge variation in vocabulary and style. So you can have domains like financial news and blogs and scientific text. So one way to approach this is just to say, okay, well, we've got multiple domains. Let's just train a model in each domain, and we can that way handle all the data we ever encounter. Well, that works well, but if you think about it, training a model usually involves some sort of annotation, and in the case of something like translation, this means you would have to go and get a translator to go and translate blogs for you. It's not something that's particularly cheap. And furthermore, it's unclear what exactly meant by domain. So obviously within blogs, there's a wide variety of different kinds of language that people use. And even within certain types, you may have blogs about cell phones versus about software. Again, where do you draw the line here? So let me sort of dive into two specific cases that I'm going to address today in this talk. The first is sentiment classification for product reviews. So in this setting, we're going to receive a review. It's just some text describing how a person felt about a product he or she bought. And the idea is we're going to want to pipe this through a statistical classifier, SVM, naive Bayes, or something, and get out a rating that's either this is positive or negative. Okay? And so I just want to pause here and say I realize that there are this has actually become a pretty hot topic in the literature, and there are lots of people now working on this. I guess there are even people at Google in New York who are doing a project on sentiment now. So where's the domain adaptation happening? We're going to look at a setting where you have annotated product reviews from one particular type of product, let's say books, where together with each review, someone went through and told me this review is expressing positive sentiment, or this review is expressing negative sentiment. But what we're going to want to do is go to a different product, let's say kitchen appliances, and apply a classifier that we learned on books. Okay? And for kitchen appliances, we're not going to have any labeled data at all. Okay, so let me give you guys two examples from these two domains just to illustrate the kinds of problems we're going to try to overcome here. So the first is from books. We pulled both of these off Amazon. So this is Running with Scissors, a memoir. This book was horrible. I read half of it, suffering from a headache the entire time, and eventually I lit it on fire. One less copy in the world. Don't waste your money. I wish I had the time spent reading this book back so I could use it for better purposes. This book wasted my life. Okay. Now let's look at a kitchen appliance review from the same site, also from Amazon. I love the way the Tefal deep fryer cooks. However, I'm returning my second one due to a defective lid closure. The lid may close initially, but after a few uses, it no longer stays closed. I will not be purchasing this one again. Okay, so if you look at the actual words that people are using to express sentiment in these two cases, actually it's quite different, right? You read half of a book, that means that you didn't really like it, but you're not going to read half of a Tefl deep fryer. Again, you don't say things like, oh, this book was defective, it just didn't work, and I'm returning it, right? That's not the way you express negativity about books. So in practice, actually, if you train up an SVM on books and you actually test it out on kitchen appliances, the error doubles. So this is a pretty serious problem. The other task that I'm going to address is more traditional, sort of canonical NLP task. This is part of speech tagging. So we're going to get some training data from the Wall Street Journal. And let me read to you guys this sentence. So this is a large corpus of annotated financial news. The clash is a sign of a new toughness and divisiveness in Japan's once cozy financial circles. And the task, again, here for part of speech tagging is to take each word and annotate it with its grammatical function. So to say something like once cozy is an adjective, toughness is a noun, and so on. And actually there are people at Penn now who are interested in building sort of NLP pipelines for biomedical abstracts, right? So they're in the biology department and they want to build NLP tools for biology text, but they don't have any labeled text, right? So they get sentences like the oncogenic mutated forms of the RAS proteins are constitutively active and interfere with normal signal transduction. Right? So again, the vocabulary really changes a lot here. What I've highlighted here are words that occur 5 times or more frequently in one domain than in another. So in particular, you have words like oncogenic, which almost never occurs in the Wall Street Journal, no matter how much text from that particular domain I'm going to show you. Okay? And the same kinds of problem occurs, right? So if you train up a state-of-the-art part of speech tagger in the Wall Street Journal and test it out on Medline, the error quadruples. Okay, so before I go into structural correspondence learning, which is the topic of the talk, I want to sort of get us all on the same page in terms of the supervised models that I'm going to be using. So these are just linear models for text, and I guess everyone here, especially at Google, will be completely familiar with them, but just to sort of get on the same page as far as notation. So the idea here is that we're going to take a document, and we're going to represent this as a vector in a high-dimensional vector space, where each dimension of the vector is a particular feature, like a word or a bigram in the case of sentiment. And for a particular instance, the dimensions which have positive non-zero values are those words which actually occur in the document. So here you say, oh, well, the word horrible occurred 3 times in this book review, I give it a 0.3. Red half occurred once, I give it a 0.1, and so on. Okay? We also have a weight vector, and in this weight vector, each weight sort of corresponds to the propensity of a particular word to indicate positive or negative sentiment. So you have things like horrible gets a -1 because it's an indicator that a document might be negative. Waste gets -1.2, and so on. And the way we're going to classify is just take the dot product of these two things, right? So this will give us a score. If we add up all the features weighted by their weights and the score is negative, we end up saying, okay, this document expresses negative sentiment. If we add them up and it's positive, this document expresses positive sentiment. Okay. So the problem I want to focus on again is, so remember we had a feature like defective, right? And we had a bunch of training data from books on which we can estimate the entries in this weight vector. But we've never seen the word defective, this particular feature. So what do? Well, the best we could possibly do is give it a 0 weight, right? We don't know, we've never seen it before, we don't know what it means, so we just give it a 0 weight. But in practice, of course, this isn't going to help us when we get to kitchen appliances. Okay, okay, so the other thing I want to mention is that, so I gave you guys a simple binary classification setting. Obviously, this is kind of the state-of-the-art for even more complex NLP structured tasks. And we'll use the same sorts of ideas, this vectorized representation, in part of speech tagging as well. Okay, so structural correspondence learning will cut this error that I was showing you guys by 40%. And the basic idea is just to use unlabeled data from the target domain. And the reason we call it correspondence learning is that we're going to induce correspondences among features from the different domains. So if we think about our sentiment example, these are things like, well, the bigram red half in books is sort of like the word defective in kitchen appliances, right? They roughly mean the same thing. Okay, and if we can find good correspondences, then the basic intuition is that the labeled data for the source domain will automatically give us a good classifier for the target domain, right? So if we do a good job at learning these correspondences, we can learn a representation that's already going to help us do adaptation well. Yeah, Sam? Mm-hmm.
One-to-one or many-to-one?
So we'll see. It's basically many-to-many. And when the algorithm gets fleshed out, we'll see exactly how that works. Okay, so actually, as far as I know, we're the first people to use this kind of idea for text. But for those of you, again, who know speech, this is a fairly common problem setup that they have there, where they want to do speaker adaptation. And there's a technique called maximum likelihood linear regression, which works pretty well for them. The setup is almost identical, but the techniques are going to be quite different. Okay, so SCL, as I alluded, is a two-step learning process. In the first step, we get a bunch of unlabeled data from both the source and target domains. And the idea is to learn a common shared representation that maps source instances and target instances into the same low-dimensional vector space. Okay? And then we're going to simply take this low-dimensional representation and learn features for that to do good classification, right? So phi now provides us with a bunch of new features, and we're just going to learn weights on those features to do our classification. Okay. So we kind of alluded to this before, but just to think about what are the properties of phi that we're looking for, well, one, we need to make the domains look as similar as possible, but also we need to allow ourselves to do classification, right? We designed our feature space to have good discriminative power. And we don't want to lose that power in doing this mapping, right? So in particular, you can think of fulfilling the first criterion by mapping all the points onto one low-dimensional point. And that's obviously not going to help us. Right? Okay, so what's the intuition for how we're going to do this? So if we go back to our example on kitchen appliances, right, there was this word defective. And we said that if we only knew that this was a negative word, we could do well here. So how could we figure out that it's a negative word? Well, let's take our unlabeled kitchen context. Again, look up the word defective in a bunch of kitchen appliances reviews from Amazon and see where it occurs, right? So you get things like, do not buy the Shark portable steamer. The trigger mechanism is defective. The very nice lady assured me that I must have a defective set. What a disappointment. Maybe mine was defective. The directions were unclear. So the words I picked here in blue are things that basically could be methods for expressing negativity about either books or kitchen appliances, right? So let's look up now these words in the book context, right? So for not buy, the book is so repetitive that I found myself yelling. I will definitely not buy another. A disappointment, Ender was talked about for some small number of pages altogether. So Ender is a character in this book that this guy really liked, and he didn't get enough face time, I guess. It's unclear, it's repetitive, and boring. Right? So again, we want to somehow use the co-occurrence with these blue features to realize that defective is like boring, number of pages, or repetitive, right, when you go to books. Okay, so what are these blue features? Well, we're going to call them pivot features, and they have several properties that I want to sort of make explicit here. First, they have to occur frequently in both domains. They need to be good at characterizing the task we actually want to do, the discriminative task. In practice, they're going to number in the hundreds or thousands. So I showed you 3, but we're going to choose many more. And we need to choose them using the data we have. So what can we exploit? Well, we have some labeled source data, and we have some unlabeled source and target data for picking these pivots. So let me give you guys 2 examples of how to pick pivots and what kinds of features come out. So the first is what I'm going to call SCL. And that's just to choose words and bigrams that occur frequently in both domains. And the second I'm going to call SCL-MI, which is like SCL, but it's based also on the mutual information with the labels. Okay. So in the first case, you get words like one, about, when, probably not such great in terms of pivots. But in the second case, when you also include the mutual information from the labels you have in the source domain, you get ones that look much better, right? Highly recommended, awful, loved it. These pivots are things that, if you could model the co-occurrences well, you would assume that we might be able to do good classification. Okay. So how are we going to actually do this? Well, the pivots, the idea behind the pivots is just to use them to align other features. So if we go back to our first example with not by, the idea here is that we're just going to cover up not by, mask it, and use the pivot features to predict the presence or absence of not by in this particular example, right? So we're going to construct a single binary problem and instantiate that across all the data and say, does the phrase not by occur here? Yes or no? Okay? And we're going to train n linear predictors here, one for each binary problem. The thing to notice here is that each linear predictor we train is characterized by a weight vector, right? And the one issue I want to point out is that these, what I'm going to call pivot predictors, are implicitly aligning features from different domains, right? How do they do that? Well, if we notice that defective and repetitive both have positive weight for not by this pivot predictor, then we know that in that case we can kind of say, well, hypothesize that these might be aligned, right? Okay, so
binary prediction task?
what's a negative example? Any instance which doesn't have the phrase not by in it. So, yeah. Okay, so we have all these weight vectors. If we construct a matrix where the columns themselves are the weight vectors from these binary prediction problems, note that actually doing the matrix vector multiplication gives n new binary features, right? Where the value of the ith feature is basically just the propensity to see not by in the same document, right? So it gives you a document back, and I get a bunch of new features which say, could not by occur in this context, yes or no, right?
Each column here is each column is the weight vector for a predictor of a pivot?
Right, exactly.
Then so you're saying ith feature is to see not by I plus 1 will be some other pivot, some other predictor that
right.
isn't not by but is.
What was the other one I listed? Awful, right?
Awful, sure, okay.
Something like this, right? Okay, so we're almost done, but we've created these 1,000 features. Let's say n is 1,000, right? If we had 1,000 pivots. But that's still reasonably large, right? And the reason I say this is that there's a lot of duplicate information here, right? You have predictors that are like horrible, terrible, and awful. All are good pivots, but they tend to mean the same thing, right? What we'd like is to have a simple basis that kind of characterizes this space, and that we can use basically as just plug into a standard linear model. Okay? And we're going to construct this by computing the SVD and using the top left singular vectors, which I'll call phi here. Okay? So for those of you who sort of know kind of history of dimensionality reduction in language, there are these two very probably most famous papers, which are latent semantic indexing and a Bayesian probabilistic variant of that latent Dirichlet allocation. I want to stop here and kind of try and characterize just at a high level what the difference is. So first, these dimensionality reductions are done on the feature document matrix. And in particular, by picking pivots, we can actually characterize the kinds of representations that we learn, right? And this actually is important, right? Because here, if we get a good representation, that's great. But if we don't, then there's no real recourse to understanding how we want to design a representation to do a particular discriminative problem, right? So by actually choosing the pivots appropriately, we can direct this dimensionality reduction to give us good features which are useful discriminatively. Okay, so now back to the second step, which is how do we use this in a linear predictor. So we have these two vectors, right? I showed you guys the high dimensional vector. Now we have the projection of this. Say we took the top 50 singular vectors. We have the projection onto a 50-dimensional real valued space. So we want to use this in our in a classifier, in a standard linear model. The way we're going to do this is very simple. We had a weight vector before for x. Now we have another weight vector for phi transpose x. I mean, we just add the two together, right? At train time, we're going to learn w and v together. And at test time, the idea is to first apply phi and then apply w and v. And the hope is that, again, the representation we learn here, phi, is good for domain adaptation. And in that case, we'll be able to classify instances in the new domain using v. Okay, so before I go into the results, I want to stop and mention two sort of direct inspirations for my design of SCL. So the first is alternating structural optimization, which is a semi-supervised technique by Ando and Zhang. And the idea there is, again, to use auxiliary predictors on unlabeled data, to train discriminative models on unlabeled data, and use that to kind of characterize a reasonable hypothesis space for doing good discriminative learning. And the second is, for those of you who know dimensionality reduction, this area of correspondence dimensionality reduction. So the idea there is that you have some high-dimensional representations of a single low-dimensional manifold, and you want to learn a manifold that respects these high-dimensional representations, these high-dimensional correspondences. Okay, so let's go on to the experimental results. So first, for sentiment classification, again, all our data is from Amazon. So we just crawled the Amazon site, and we pulled down a bunch of reviews. These are books, DVDs, kitchen appliances, and electronics. These are our 4 domains. We had 2,000 labeled reviews from each, and between 3,000 and 6,000 unlabeled. And so we treat this as a binary classification problem. Each review has together with it a set of stars. And we take things that are 4 or more stars, 4 and 5 stars, and call them positive, 1 and 2 stars, and call them negative. Okay. Mm-hmm.
When you say unlabeled, do you mean you downloaded the stars for those 3,000 to 6,000, but you don't show them in the algorithm?
Right.
There's some reason why in the data set you don't believe those labels.
No. There's no reason, actually. We could, in fact, use them as labeled. This is purely for experimental purposes. So, I mean, well, that's not quite true. We sort of curated and tried to throw out duplicates and do a good job at finding reasonable reviews for our labeled data. But basically, they come from the same ultimate source. Okay, so the features, we use unigrams and bigrams, which is pretty standard for this task.
So the technique you're explaining, does it assume that the domains are given, that you're going to tell it this text is in this domain, that text is in that domain, or are you able to to generalize across text where the domain itself is unlabeled?
So all the experiments I'm going to show you are from the first case. But we can actually talk afterward about, firstly, potentially discovering multiple domains and also using the same sorts of ideas here when you have no idea where the domains are segmented. So both of those are things we've looked at, but they're not part of this talk. Okay, so for the pivots, we're going to use SCL and SCLMI, which I showed you guys several slides back. And at train time, we're just going to minimize Huberized version of the hinge loss. You can use whatever your favorite loss is. Okay, so before I show you the numerical results, I want to show you kind of visualization of the kinds of projections that could potentially come out of this sort of learning procedure. So the first is, so what I'm showing you in the top left here are words that only occur in the books domain and are negative under this projection. Right? So this is a single column of phi. Plot, if you talk about the plot, you don't like the book. If you say something's predictable, that's not a good thing. For kitchen appliances, the plastic, if the little plastic handle breaks, books typically aren't poorly designed, although they could be, but kitchen appliances, if you don't like it, you say it's poorly designed. Leaking, books don't leak. Positive, you have fascinating, engaging, must read. Grisham, people like John Grisham on Amazon. For kitchen appliances, espresso is sort of like the John Grisham of kitchen appliances. People just like espresso. And you have other words like are perfect. Using this was a breeze. I've been using it for years now. All these are ways of expressing positivity that are specific to appliances, right? So the nice thing about this, other than just being cute, is that actually remember that we're going to want to train a discriminative model here. And even if we've never seen all these words on the bottom, we can tell that poorly designed, for instance, expresses negative sentiment by virtue of the way it's projected relative to plot, predictable, and number of pages. And we do have labeled data for these, right? So we can actually tell this immediately from our labeled data. OK. So here are the first set of numerical results. They're kind of complicated, so let me parse them a bit. First, what I've labeled up top, each of these sections, is one domain that we're going to adapt to. So this is testing on books here. This 80.4 is the result we would get if we took all 2,000 labeled data points and trained a classifier on that in books. So this is sort of like the upper bound. How well could you do if you had a good books classifier, right? Each of these sets of 3 bars is training in one particular other domain. So again, like electronics and kitchen are not very similar to books. DVDs are more similar. So in general, the bars are higher. The baseline is what happens if I just train an SVM and test it. The blue is what happens if I use the SCL features, and the green are what happens if I use the SCL MI features. So the thing, this sort of takeaway message here is that in particular, how to interpret these, if you look at this set, the baseline loss due to adaptation is 7.6%. The SCL MI loss is around 0.7%. So you can do almost as well as having books using only unlabeled data from the books domain and lots of labeled DVD data.
I mean, these are great results. I'm not trying to be negative about it, but I just want to understand the red line labeled 80.4 doesn't get to see the pool of unlabeled data that the green and blue bars got to see, right?
That's right. So potentially,
in principle, if someone thought that they were a semi-supervised learning genius, they might claim that they could push the red line up a little bit.
Yeah, actually, you can push it up quite a bit. And I'll show this. Typically, you can't push it up. Well, OK, you can push the red line up. Yeah, I mean, it depends how much labeled versus unlabeled data you have. No, you're right. We'll show sort of adaptation versus semi-supervised learning in the next set of results. But I don't have numbers for this particular task. So OK, so one way to sort of point this out is actually on kitchen and electronics, right? So these are really similar. Kitchen appliances are almost all kind of electronics, right? So like both of them can be defective. A lot of the words are the same. So here, you do get this kind of semi-supervised result, where if you add a lot of unlabeled data, you can actually do better than the sort of gold standard here, the red line. OK. But the thing I want to focus on briefly here is the screw-up, right? So somehow we actually did worse using SCL than not using the unlabeled data at all. Right? So what happened is basically we somehow managed to misalign features from the 2 domains. Right? So you get things like, well, there are you're learning a representation from unlabeled data. So there's a lot of variance in book reviews. Some of it is whether or not someone's positive or negative, but a lot of it is like, well, this is a Christian literature book, and this is a fiction book, and this is a nonfiction book, and this is a self-help book, right? So a lot of things you see, a lot of these mistakes that you see are basically projections that look reasonable for kitchen appliances, but on books are actually kind of doing topical discrimination. Okay, so we thought about how one might go about possibly fixing this. And we said, well, what could you do with a minimal amount of labeled data? If you were just a guy who wanted to quickly prototype something, what could you do with 50 instances, right? So this is 50 versus 2,000. Again, we're assuming that we're using the same training procedure before, so here's what we're going to do. We're going to train on the source data, save the weight vector here, v sub s, for the SCL features, the low-dimensional features. Now, on the target data, we're going to simply regularize the weight vector to be close to the weight vector we had from the source domain. Okay? So if you look at this as an optimization problem, the first term is just the hinge loss that we had before. The second term, we want to encourage not using the high-dimensional features as much as possible, right? With only 50 instances, it's unlikely that we're going to get a feel for the kind of vocabulary you see in the new domain. But on the other hand, we might be able to learn something reasonable about the low-dimensional features, right? So the idea here is that we want to keep the SCL weights as close as possible to the source. We believe that it's mostly right, but we want to correct the few things that we did wrong, right? And we're going to do that by trading off basically this first term from this last term. Okay? So this technique actually is based on an idea from Chelba and Acero. Chelba is now here at Google. I guess he's in Kirkland. I don't really know. They actually proposed regularizing on the high-dimensional weight vector, right? So the place we differ from them is that we're actually, we advocate using the low-dimensional features. We think that by having this low-dimensional representation, you can get a lot more power out of the small number of labeled instances you have. Okay, so here are the results. Basically, the baseline is exactly the technique of Chelba and Acero. The idea there, again, is to regularize based on the high-dimensional features that you had. Our technique is this variant where you only try to match the low-dimensional features to what you learned in the source domain. And in this case, SCLMI always improves over the baseline for every pair of domains that we have. Okay, so I showed you guys a bunch of results here, and I want to kind of help distill them. So first, even without any unlabeled data, we reduce error due to transfer by 36%. And the thing I want to point out is that if you have just 50 instances and you use this other technique, basically it doesn't work at all. And that's because 50 instances just isn't enough to help you with such a high-dimensional weight vector, hundreds of thousands or millions of features, right? But if you have a good low-dimensional representation, you can further improve to a 46% relative reduction in error. Okay. So the other task that I want to talk about is part of speech tagging. And so for this task, the data that we're going to look at is quite a bit larger. So we have 1 million labeled words of Wall Street Journal text, and we're going to add 2 or 3 million words of unlabeled text from the Wall Street Journal and from Medline. Okay? And again, the task is to train a tagger in the Wall Street Journal and test it on Medline. Okay? We're going to use as our supervised learner what I'll call Myra CRF. Basically, the idea here is that you want to separate the highest scoring, the best label from the top highest scoring incorrect labels by a margin. And there's a good JMLR paper that describes this that I highly encourage everyone to read. And so the other thing that I want to specify here is what we choose for pivots, right? So I'm going to focus on sort of the word-by-word representation. So if you look at a 3-word window, what we're going to use for pivots are common left, middle, and right words across domains. Okay.
Also with mutual information about the
Actually, so here there's not. We have results for that, but I'm not going to show them here. They do. It does slightly better when you use mutual information. Okay. So, all right. So now the same visualization of the projection onto a single dimension from phi. So only in Medline you get words like receptors, mutation assays, and lesions negative under this projection. Only in Wall Street Journal, company, transaction, officials. Only in Medline that are positive, metastatic, neuronal, transient, and functional, and versus political, short-term, pretty. So what is this projection doing for us? Well, it's separating nouns on the negative side from adjectives and determiners on the positive side. Okay, so again, the takeaway message is that even if we haven't seen any of these words here on top, we can do a good job at discriminative learning by using by using their projection onto this line and the similarity with these other words that we do have lots of labeled data for, the Wall Street Journal words, right? Okay, so here the set of results comparing sort of semi-supervised with SCL. So the black line here is just train a Myra tagger on the Wall Street Journal. The blue line here is train the semi-supervised method of Ando and Zhang, this alternating structural optimization, and the red curve here is SCL. So the first thing I want to point out is that if you don't have very much labeled data at all in the Wall Street Journal, so these are learning curves for a number of Wall Street Journal sentences. So you don't have very much data at all, then you can get a nearly 20% improvement, reduction in error for part of speech tagging. But even when you have a lot, so MX post is another baseline that I just wanted to throw up there. This is Adwait Ratnaparky's part of speech tagger, and it's sort of the standard out-of-the-box tagger that one would use if you wanted to work on this problem. So here actually there's you can still significantly improve over all these methods. And one interesting thing is for unknown words, right, where you actually don't know, you've never seen this word before, and this is kind of what we've designed for, you can actually get a more than 20% improvement, even with 1 million words of labeled Wall Street Journal text. Okay. Again, so there are other methods for incorporating labeled data in this setting, and in particular for these kind of what are called structured problems where you have a label that's more complex, you can potentially use the output of a tagger trained in the source domain as a feature for the target domain. So this was advocated by Florian et al. NACL a couple, I guess 3 or 4 years ago. The idea here is that we want to just, so how are we going to compare SCL with a normal supervised tagger? We just want to train one of these taggers in the source domain and use it as a feature in the target domain and see how much improvement we can get. Okay, so looking at that, this thick black line here is not using any target data at all. So we just ignore this data. That's why the curve doesn't go up. We just train a source tagger. This dotted line is what happens when you use a small number of in-domain training instances. And here what I'm showing, the blue line is the supervised tagger, and the red line is SCL, right? Using this, combining it with the target data using the same idea of Florian et al. So again, like for this side of the graph, you can get a nearly 40% relative reduction in error. So from something like 86 to 91 by using SCL and together with the this trick of using features of the source tagger. But even for a large amount, notice here actually using the source data doesn't help you at all versus not using it. But once you train the source tagger with SCL, even with a fairly large number of Medline training sentences, you can still get a significant improvement. OK. So I want to end on a somewhat speculative note for various people in this audience that maybe we can talk about afterward. So first is machine translation. I know there are a lot of people working on this here. The basic scenario I'm envisioning is where you have some domain-specific parallel text, like news or legal text or UN transcripts, what have you. And but what you want is to actually do translation in a very different domain, like let's say blogs. And there you may have actually lots of similar corpora, right? People write blogs in Chinese, people write blogs in English, but they don't often translate them. And you want to exploit all this unlabeled data. So I could envision exploiting it in two ways, and I'll talk about we can talk about the specifics of that offline. But basically, you can obviously adapt a language model, and people have worked on this. But you could also conceive of learning new translation rules based on similar contexts to the source data that you have. Okay, the other obvious problem for this audience is search ranking. So I can kind of envision a scenario where you have a query and a list of top-ranked documents already. Right? What you want to do is re-rank them based on some features of the document and the query. Right? So, and you may have some labeled data either in the form of editorial data or in the form of click-through data. And the adaptation here is, well, you might have very different markets. So in particular, you may have lots of good editorial data for English, but in Indonesia, you have barely any. Right? And yet you still want to be able to exploit this in a reasonable way. And the pivots I'm envisioning here are just common relevant features across the different models. Right? So you may have features that are relevant in both domains and a bunch of other features that you don't really know about. You want to somehow align these features. Okay. So, and finally, for those of you who are more into sort of learning theory, we have some work on that as well that I would be happy to talk about. So the idea here is that you have a model that you've trained on one particular distribution and you're going to test it on another. Can we prove learning bounds on the error of that model in a new domain? So we have a couple papers on that. OK, thanks. Yep.
I was just curious, like the idea of this structural correspondence learning is basically trying to pick up the pivot features and then cast the features that you don't see in the training data into those feature space and do a low dimensional reduction and then train a model on that.
Right.
Do we still, like in the learning times, you have sort of two set of parameters, one for original things, one for those pivot related features. Do you still need the first parts?
Yeah, so that's a good question. Actually, you do need it in the sense that it improves results. So the reason for that is that there are some things which, doing unsupervised learning, you just aren't going to model well. And you need to kind of pick up the slack there. So we have done experiments using just the low-dimensional representation. And basically, that kind of does in between the two. So wherever the results I showed you are, if you use just the low-dimensional representation, it's usually a little better than using the high-dimensional, but not as good as using both. Mm-hmm.
In thinking about the domain of book reviews, I'm wondering about the significance of two sources of noise and sentiment that I can imagine.
Mm-hmm.
One is irony, where somebody uses irony in a review, the sense of their sentiments might be flipped from what it appears from
Yes.
the word analysis.
Right.
The other one is that books themselves are often criticisms or praising of various topics. So in discussing a book, independent of your sentiment of the book, you might be using criticism or praise words in discussing the content of it.
Mm-hmm. Yes, so first, these are problems for sort of sentiment analysis in general, independent of the particular method that you use. But I absolutely agree with you. These do come up. In our experience, it's quite rare. But you have to understand that someone going to Amazon and writing "I lit the book on fire" is not the New York Times review of books, right? They're not going to express sentiment in quite the same way. But you're right that it is a potential problem, and I think this is one reason why you don't see numbers as high as you would expect for binary text classification, right? So after 2,000 instances, if you look at, I don't know, some other text classification problem, the Reuters task, right? You're almost always well above 90, right? Here you're not going to see that because there is quite a bit of noise, and that you're right. I mean that's something that you have to deal with. Mm-hmm. Sam.
So in the feature selection, that seems like selecting the pivots is very important here.
Yes.
So when you do the mutual information, is it that you have to have in your own domain high mutual information with the class, or do you also have to have high mutual information? You understand my question?
Yes, I understand your question. So I didn't say that, but you're absolutely right. The assumption is that mutual information with the label is the same across domains. So you can violate this a little bit, but in cases where you violate it a lot, you're basically screwed. So you can envision instances where there's some adversary that basically takes the best linear predictor in your source domain and flips all the weights, right? Then there's just nothing you can do from that and unlabeled data, right? In practice, I think that it seems like in all the problems I've looked at, both these and a few others, you don't see this kind of flipping a lot. So the mutual information assumption seems reasonable.
You get things that commonly co-occur in both domains, and then you filter by mutual information, again, in both domains.
Well, no. We don't have mutual information in the target, right? So we just assume that by filtering in the source and using the commonality, you also got features that are highly informative in the target. Yes, the com.
You use the 100K unsupervised data.
Mm-hmm.
What prevents you from using like 20 times that?
So nothing. Basically, there is such a large. So one is we're limited by the amount of data we can actually get access to. Obviously, you guys have much more than we do on our computers, but there is a larger version of the Wall Street Journal which has 30 million words, and which we are using for a separate entity recognition task, and it works well for that. There's no, in terms of scaling, there's no reason why this method can't scale up. In fact, training the predictors are, of course, is completely parallelizable. So you could do that fairly easily. Yes?
Yeah, I was wondering how this would apply to texts that do not work well with parse speech taggers. For example, like blog comments, very short, maybe not grammatically correct ones. Yeah.
So again, the basic assumption, the underlying assumption here is that there is a sort of single good model for all these different domains, right? So it doesn't have to be a model that you can train in one, but the idea is that if I had a lot of, blog comments to train on, and I had a lot of Wall Street Journal text to train on, then I could train a single good tagger that was good at both, right? If I can't, if for some reason, when I say the word dog in a blog, it's an adjective or a verb, right? There's slang usages that probably would be particularly difficult to get. That would be problematic. But I think, I would love to try this out on more widely varying domains. And actually, the Medline is pretty different. It's there are really some things where I look at it and I look at it myself and say, I have no idea how to tag this. I have no idea what these people are talking about. Right? So, yes, I guess both here.
Well, we have different questions again. But did you try the approach of training in one domain, then using the classifier of the other domain, taking the ones for which it expresses strong preference, and then retraining on this?
Yes. So yes, we did. This approach is often called self-training, and it can work very well sometimes. It can break horribly sometimes. So I think this is one problem with these sort of bootstrapping approaches to semi-supervised learning or to using unlabeled data. It's that you can potentially introduce a lot of noise and ruin the model you had before. So in our experience, there are some tasks for which it works really well, and some for which it actually works quite a bit worse than a model that used only labeled data. There is a paper at this year's ACL by Chenxiang Zhai and one of his students that basically study a bunch of these other approaches, and they look at self-training as well. So you can sort of go look at that for other references to self-training. Yeah.
So one question is, can this adaptation be thought of as learning a translation, like table from domain 1 to domain 2 for the important words?
I mean, at a high level, it's possible. I don't want to commit to that, in part because I'm not an MT guy and I don't really know, but in part because I think part of the power of this method is that a lot of these features are bad, right? A lot of the projections, phi, are actually noisy, right? But by having a good discriminative model to train on, you can overcome that, right? So it's sort of like, if you had a hard alignment, it's almost like doing hard clustering, right? You throw out a lot of information you had, and you could potentially have used that information to recover a good discriminative model, right? So, I mean, I do think that having actually this sort of soft projection onto a low-dimensional real-valued space is very important. Peng. Okay, sorry.
I was wondering, so for the selection of pivot, you have two factors basically. You have one, is it a good predictor for the final task?
Right.
And you have one other which is kind of regularizer. Does it appear frequently? Which would mean that it might be also a good predictor for the second task. For the second
That's right,
domain.
yes.
So I was wondering if, to measure is a term a good predictor? If you have a linear classifier, you have actually the derivative, that is to say the effect of removing the word in the weight itself. So could you use that instead
Yes,
of
you have. So there are lots of ways of doing feature selection, and mutual information is by no means the best one. I don't actually want to commit to saying I love mutual information for feature selection. Actually, I would be interested in looking at either that criterion or, I mean, obviously L1 regularization is a good criterion for doing feature selection. Any of these, I think, have the potential to be even better by accounting for common dependencies among the features, right?
So did you try that? Or?
No, I haven't tried that. Yeah.
Yeah, I have actually two questions.
Mm-hmm.
One is, how important is the choice of pivot features? For example, do you have any thresholds or parameters to control the size of features?
So the actual identity of the pivot features is very important. The number of pivot features is actually not so important. So there are basically two criteria that you need to kind of trade off. One is that you need enough pivot features to basically characterize the kinds of space you're in terms of training these predictors. The other is that each individual predictor, you need to get good statistics for it on the unlabeled data. right? So if a particular, if you say to go to include all the features, then you have maybe some features which only occur once or twice, even in a huge amount of unlabeled data. You can envision, I don't know, 10 grams or something, right? In that case, it's hard to actually train a good predictor that generalizes well. And so this is why we choose sort of only the frequent ones.
If you have many, like you change the direction of the SVD because you can't like one, the error is weighted the same on each weight.
The error's weighted the same, but actually this is exceptionally important because you can get a much higher margin if you have, you know, fewer instances to deal with, right? So if you think about the kinds of loss, you know, I mean, higher margin basically corresponds to a smaller weight vector, right? So if you can train something, and the magnitude of the weight vector actually does appear in the SVD. Right?
So the second one is if you use the adapted model to the original domain, how much worse do you do, or do you do worse?
You typically don't do worse. And the reason for this is that, for a couple reasons. One is you have all the features from the original domain. Sometimes you can do better if the domains are similar enough. You have all the features from the original domain to sort of, if you happen to learn a representation that's not so good, you can recover that because you have the original feature space, right? The other reason, though, is that you know, if these domains are so high dimensional, right? The feature space is so high dimensional that actually, for text, there usually is one good model, right? There typically is one, you know, reasonable model for sentiment. Of course, there are these words that, you know, irony, or words that switch polarity in domains. You know, something like predictable, right, is very good, is bad for books, but actually your kitchen appliances, you want them to be predictable, right? But there aren't that many of those kinds of words. So you typically you can do as well as or better in the original domain.
Do you have a way of detecting that kind of word and throwing it out? Say?
No. I mean, they're heuristics you can use, but none of them are really good. You know, you can sort of say, oh, well, predictable in kitchen appliances co-occurs with a lot of words that seem to have positive sentiment, but in books, negative. But there's nothing, I haven't found one good heuristic that seems to work well all the time.
Like, do you need to apply the SVD before you try to train that combined model? Like, what if you didn't do SVD? Because you can basically put some regularization on top of it. And
yes, so you can. It doesn't. So empirically, it doesn't work as well. And I don't have any really good theoretical justification of that yet. I actually hypothesize that the reason the SVD is important is that you actually don't really care about predicting the pivots themselves, right? And in fact, that can cause you to kind of overfit to the pivots. What you want really is to be able to sort of predict kind of somewhat nebulous general positive or negative sentiment, right? So there really is a low-dimensional underlying representation that you want. That's why I think the SVD is important. How to characterize that formally is
like,
future
what's
work.
the sort of performance difference we're looking at, like in terms of the 46 reduction?
Oh, instead of 46, I actually don't know sort of the across the board, but it tends to do about half as well. So you still get an improvement, but it's not as big. Like it's right in between the two. I didn't do sort of the extensive averaging or cross-validation that I did for these actual numbers that I'm showing here. So, okay, thanks.